Hi everyone, I'm Sam, and today we're going to talk about agriculture. If human history were a 24-hour movie, the emergence of agriculture would happen at around 11:45 p.m. For most of our time on Earth, humans lived as hunters and gatherers, tracking animals, foraging for wild fruits, and struggling against nature. Then, around 10,000 BCE, a profound and irreversible shift quietly began in a region we now call the Fertile Crescent, located in present-day Iraq. People started to sow seeds, cultivate land, and, like wild grasses, patiently wait for the seasons to change. This transformation later became known as the Neolithic Revolution. Why did humans give up the flexible life of hunting and choose to settle on one piece of land, taking on the risks of droughts, floods, and failed harvests? One possible answer is climate change. After the Ice Age ended, the climate became more stable, making farming more feasible. Another driving factor could have been population pressure. At some point, humans began developing a new way of producing food called crop domestication. This meant selectively breeding wild plants to make them more suitable for human use. Seeds became larger, sweeter, less prone to falling off, and easier to store. These plants no longer evolved on nature's terms. They began to depend on humans for reproduction and care, becoming the backbone of early agriculture. Domesticated crops began to emerge independently across different continents. Rice and millet in China, maize in Central America, potatoes in the Andes, sorghum and pearl millet in Africa, all born from their unique environments. Domestication didn't just change the genes of plants, it transformed human life. Settlements gave rise to villages, villages grew into cities, and agriculture laid the foundation for civilization itself. But farming also introduced new challenges. Soil became exhausted, pests spread, and monocultures were vulnerable to disease. In response, farmers began to explore how to let the land rest and rotate usage. By medieval Europe, a method called the three-field system had taken shape. Land was divided into three parts, rotated between winter crops, summer crops, and fallow land. This practice not only protected the soil, but also improved overall yields. It was more than an agricultural innovation. It was a strategy for organizing society and labor, allowing farmers to work and rest with rhythm and structure. This journey, from wild grass to cultivated rice, was humanity's first real attempt to rewrite nature's rules. It sowed the seeds for millennia of civilization to come. Agriculture has never just been about planting crops. It reshaped our relationship with nature, with time, with space, and gave humanity, for the first time, the power to shape the future. In 1492, when Columbus arrived in the New World, he set in motion the largest biological exchange in human history. Potatoes, corn, tomatoes, cocoa, and chili peppers crossed the Atlantic and made their way into the kitchens of Europe and Asia. In return, wheat, rice, grapes, coffee, and horses flowed in large numbers from the Old World to the Americas. This intercontinental food migration later became known as the Columbian Exchange. This exchange didn't just enrich European cuisine, it redrew the agricultural map of the world. In less than 2 centuries, potatoes from the Andes had become a staple in Ireland, maize from Mexico spread rapidly across East Asia and became a key crop in southern China. Sugarcane, tobacco, and cotton rose to global prominence, shaping international trade and profoundly impacting social structures and economic systems. Agriculture became closely tied to empire building, commerce, capital, and power, emerging as one of the driving forces of globalization. At the same time, European thinkers began to reconsider the nature of agriculture itself. In 17th century England and the Netherlands, the first systematic studies of soil, plants, and crop rotation were conducted by early agricultural scholars. Reformers like Jethro Tull advocated for seed drills, deep plowing, and the replacement of tradition with science, promoting the idea that agriculture, like machinery, could be improved. These ideas set the stage for the British agricultural revolution in the 18th century, which significantly boosted productivity and freed up rural labor for the coming industrial revolution. This was the beginning of an era where knowledge and land began to merge. Scientists no longer focused solely on astronomy or geometry. They turned their attention to soil, crops, and livestock. They observed growth patterns, recorded climate and pest outbreaks, and began experimenting with data and trials to improve farming methods. It was a quiet revolution, but one with far-reaching consequences. Agriculture was moving toward a more rational, technical approach, even if it was still far from the scale and efficiency of modern farming. Columbus brought the seeds. The agronomists planted the ideas. Together, they sparked the early stages of agricultural modernization, a process combining the movement of plants with the transformation of knowledge. And all of this was still just the beginning. In 19th century Europe, agriculture was facing a crisis that was visible to the naked eye. As populations grew and cities expanded, the demand for food soared, but crop yields failed to keep pace. Farmers noticed that their land seemed to become increasingly barren, and even traditional fertilizers like animal manure and ash could no longer stop the decline in harvests. At the time, people didn't understand why. It was all left to the mercy of the weather and the grace of the gods of the soil. In the midst of this uncertainty, a German chemist named Justus von Liebig turned the cold light of the laboratory onto the fields. He wasn't a farmer, but a scientist who studied chemical reactions. Yet he posed a question that would transform the future of agriculture. What exactly do plants eat? In his 1840 book, Chemistry in its Application to Agriculture and Physiology, Liebig introduced the idea of plant nutrients. He argued that plant growth wasn't powered by some mysterious natural force, but by specific chemical elements absorbed from the soil, like nitrogen, phosphorus, and potassium. His most influential theory became known as the law of the minimum. A plant's growth is limited not by the total amount of nutrients available, but by the one nutrient in shortest supply. Just like a barrel can only hold as much water as its shortest stave allows. This theory gave farmers, for the first time, a way to diagnose soil deficiencies and target them with specific supplements. It wasn't just a theoretical breakthrough. It laid the groundwork for the modern chemical fertilizer industry. Although Liebig himself failed to produce an effective artificial fertilizer, his ideas reshaped agriculture. It was no longer merely a traditional craft based on experience and intuition, but an applied science that could be measured, tested, and optimized. Liebig probably never imagined that the seed of chemistry he planted would one day blossom into an entire industrial-scale system that would reshape nature itself. The elements he studied in glass flasks would become not just nutrients for plants, but the lifeblood and the limitations of modern agriculture. By shifting the focus from observing nature to analyzing it scientifically, Liebig helped us understand for the first time what plants actually eat. And in doing so, he led us to ask a deeper question. What does what we feed them mean for the land and for our future? While Liebig's theory highlighted the crucial role of nitrogen in plant growth, it also left behind a major technical challenge. How can we extract the nitrogen that plants need from the seemingly endless supply in the air? That question puzzled scientists for decades, until the early 20th century when a breakthrough finally came. Although 78% of the air is made up of nitrogen, plants can't make use of it directly. They can only absorb nitrogen in specific forms that are naturally converted by a small group of soil-dwelling bacteria in a slow and limited process. So despite the abundance of nitrogen in the atmosphere, usable nitrogen in the soil was often in short supply. Liebig understood its importance, but he couldn't solve the puzzle of how to deliver atmospheric nitrogen to plants in a usable form. The solution came from two Germans, Fritz Haber, a theoretical chemist, and Karl Bosch, an industrial engineer. Haber developed a method to synthesize ammonia directly from atmospheric nitrogen, and Bosch scaled that method into an industrial process. In 1910, the Haber-Bosch process was born. The first time humanity could extract large quantities of usable nitrogen fertilizer straight from the air. The significance of this invention is hard to overstate. It transformed the scale and potential of agriculture, freeing farms from the limitations of natural fertilizer supplies. By some modern estimates, nearly half of the food consumed by the world's population today depends on synthetic nitrogen fertilizers made through the Haber-Bosch process. In other words, this single innovation helped fuel the population explosion, from under 2 billion people at the start of the 20th century to over 8 billion today. But the technology came with a dark side. Haber later developed poison gas weapons for Germany during World War I. Bosch's company, BASF, and its successor IG Farben were deeply involved in wartime production and forced labor during the Nazi era. On a technical level, synthetic nitrogen fertilizer, while boosting short-term yields, has also caused soil acidification, water pollution, and greenhouse gas emissions, environmental issues that now haunt modern agriculture. The Haber-Bosch process is a paradoxical technology. It is both the tool that feeds the world and one of the root causes of 21st century environmental crises. For the first time, humanity could create food from air, a miracle once imagined by alchemists. But it has come at a cost. It's as if we made a deal, short-term abundance in exchange for long-term risk. We've learned how to feed the planet with science, but now we must ask, can this kind of abundance last? If the Haber-Bosch process was about creating food from air, then genetic engineering is about stepping directly into the heart of life, rewriting the code of plants themselves. This time, humans aren't just breeding higher-yielding crops, we're redefining what a crop is. This revolution began in the 1980s and quickly moved from the laboratory into the fields and into heated debates about nature, risk, and power. Traditional breeding involved slow generational selection. Genetic engineering, by contrast, allows us to cut and paste genes from one organism into another. For example, beet corn carries a gene from a soil bacterium that produces an insect-killing protein, allowing the plant to resist pests without frequent pesticide spraying. Another example is herbicide-resistant soybeans, which can survive chemical weed killers that eliminate surrounding weeds but leave the crop unharmed. In 1994, the U.S. approved the first genetically modified food for sale, the flavor savoir tomato, engineered to delay ripening, a symbolic beginning of a new era. Since then, GM crops have rapidly spread across the U.S., Brazil, Argentina, China, and India, primarily in key commodity crops like corn, soybeans, cotton, and canola. Supporters argue that these technologies increase yields, reduce pesticide use, and help small farmers withstand drought and disease, offering powerful tools in the fight against global hunger. But criticism has never gone away. Opponents point to risks such as ecological disruption, food safety concerns, and intellectual property disputes. Many GM seeds are protected by patents, preventing farmers from saving and replanting their own seeds. They must purchase them from large corporations each year. What was once a shared agricultural resource, seeds, has increasingly become a form of corporate-controlled capital. This debate over genetic modification is not just a scientific one. It's deeply philosophical and political. How do we define nature? Should the future of agriculture be determined by sequences in a lab, or should it return to ecosystems and local knowledge? Despite the ongoing controversy, genetic engineering has clearly become a part of agriculture. It's more than just a technical innovation. It's a choice of values. In changing the genes of crops, we're also reshaping our relationship with land, food, and the future itself. But agricultural innovation hasn't stopped at genetic engineering. In the fields of the 21st century, another, quieter yet equally profound transformation is underway. Instead of simply changing what crops are, we are now changing how we grow them, how we make decisions, and how entire farms are managed. Imagine a world where a farmer can sit in front of a computer and monitor the growth of every single plant, adjust irrigation in real time, apply fertilizer with pinpoint accuracy, and predict pest outbreaks before they happen. This kind of farming looks less like trudging through muddy fields and more like piloting an aircraft. And it's not science fiction. It's the emerging reality of modern agriculture, often called precision agriculture or smart farming. At the heart of precision agriculture is data-driven decision-making. This digital transformation began to take shape in the early 2000s, spurred by the rise of GPS technology, drones, soil sensors, weather forecasting systems, and AI algorithms. Farmers no longer rely solely on experience and intuition. They now have access to real-time field data, soil moisture, nitrogen levels, sunlight patterns, pest activity, and more. For example, in the vast cornfields of the U.S. Midwest, farm machinery can now adjust seeding density and fertilizer amounts automatically, based on maps and historical data. In Israel's desert agriculture, Drip irrigation systems powered by AI deliver water in milliliter precise amounts, tailored to each plant's needs. Across Asia, more and more rice farmers use smartphone apps to monitor field conditions and receive early warnings about extreme weather events. This shift toward precision helps reduce costs, improve efficiency, and lessen environmental impact. Overuse of pesticides and fertilizers has long been one of modern agriculture's biggest environmental issues. With precision control, resources can be used exactly where they're needed and nowhere else. In a world facing climate change and limited farmland, this may seem like a timely solution. However, precision agriculture also comes with challenges. The technology is often expensive, placing it out of reach for smallholders and farmers in developing countries. In addition, the rise of centralized data systems and agricultural platforms raises new questions. Who owns the data? Who profits from it? As farms become massive digital networks, farmers may risk losing control over their land, not physically, but informationally. Precision agriculture is a revolution about a visible future. It brings knowledge, technology, and land into close alignment, but it also reminds us of a crucial truth. Technology is never neutral. It creates efficiency, yes, but it can also deepen inequality. As digital technologies make their way into the fields, humanity has also begun shifting its focus from how to grow food more efficiently to reimagining food itself. One of the most controversial and disruptive innovations in this shift is the reinvention of meat. Imagine a hamburger patty that wasn't cut from a cow, but grown in a lab. This is cultured meat, also known as lab-grown meat or cell-based meat. It's not plant-based imitation meat. It's real animal muscle tissue, but produced not through slaughter, but through science. The process begins by extracting a few living cells from an animal, which are then placed in a nutrient-rich solution where they divide, multiply, and gradually form muscle tissue, eventually growing into something that looks, cooks, and tastes like meat. No animals are killed, and in theory, it uses far less land and water while dramatically reducing greenhouse gas emissions. The development of lab-grown meat isn't just a scientific milestone. It forces us to rethink what we mean by meat and to re-examine the ethics of what we eat. Advocates argue that cultured meat could put an end to the cruelty and pollution of industrial livestock farming and offer us a sustainable solution to future food shortages. In a world of shrinking resources and rising concern for animal welfare, it seems like a promising middle path. But challenges remain. The cost of producing cultured meat is still high, and the technology hasn't yet reached full commercial scale. Most products are not yet affordable or widely available. What's more, many people instinctively distrust the idea of meat grown in a lab, raising questions about its naturalness, safety, and even whether it might displace traditional farmers, deepening economic inequalities. Will lab-grown meat become the centerpiece of our future meals? It's too early to tell. What's certain is that we're at a crossroads, where science and ethics meet, and beginning to ask big questions about what real meat is, and what a truly sustainable lifestyle could look like. Lab-grown meat may not be the final answer, but it's likely the starting point of a much larger conversation, one that could reshape not just our diets, but our relationship with food, animals, and the planet. In the 21st century, agriculture faces a double challenge. On one hand, we need to feed more than 7 billion people, a number expected to reach 10 billion by the middle of this century. On the other hand, agriculture itself is being severely impacted by climate change and has also become one of its major contributors. The relationship between farming and climate is no longer just one of victim and weather, but a deeper, two-way interaction that calls for a new distribution of responsibility. Crops around the world are now facing increasingly unpredictable extreme weather events. Droughts, floods, hurricanes, and heat waves are growing both in frequency and intensity. Yields of staple crops like wheat and corn are becoming more volatile, leading to fluctuations in global food prices. Farmers in the global south are often hit hardest, living in the most climate-vulnerable regions, yet with the fewest resources to adapt. At the same time, agriculture is also a driver of climate change. According to the UN's Food and Agriculture Organization, agriculture, forestry, and land use account for more than 20% of global greenhouse gas emissions. This includes methane from livestock, nitrous oxide from fertilizers, and carbon loss from deforestation. When we clear rainforests to grow soybeans or palm oil, we're not just producing food, we're dismantling the planet's carbon storage system. In response, a wave of new ideas and practices known as sustainable agriculture has emerged. Regenerative agriculture aims not just to avoid harming the land, but to actively restore its health. Carbon farming seeks to increase soil carbon storage through techniques like no-till farming and organic mulching, turning agriculture from a problem into a solution. Agroecology emphasizes biodiversity and the integration of local knowledge into farming systems. Still, the core question remains: can the Earth continue to feed this many people? The answer may not be a matter of technology alone, but of distribution, consumption, and values. If we continue wasting food, over-consuming resource-intensive products, and allowing farmland to be squeezed by industry and urban expansion, then no amount of innovation will be enough. Agriculture is not just about how we produce food, it's about what kind of life we choose to live. Climate change has made this question urgent and unavoidable. The future of farming isn't just in the hands of farmers, it's in the hands of all of us, through the choices and responsibilities we carry each day. That's it for today, and I'll see you in the next episode.